Hi, everyone. Welcome to the Practice Platform Seminar initiative by the M&SOM Practice Department as part of the journal. The goal of this seminar is to bring voice of practitioners closer to the operations community. And today we have Anna Radovanovic, who is going to speak to us about carbon-aware computing at Google and beyond. So I have the pleasure of introducing Anna. Anna is a senior staff research scientist serving as a technical lead for the energy analytics and carbon-aware computing at Google. She has been a researcher at Google since 2008 and earned her PhD degree in electrical engineering from Columbia and worked for 3 years as a researcher in the math sciences division, which is where I am currently, but now it's called the AI division. For more than 12 years, Anna has focused all her research efforts in building innovative technologies and business models and is considered a thought leader in decarbonizing the electrical grid and delivering clean energy to the world. Just as a matter of logistics, the seminar will be recorded and will be available through the Informs YouTube channel, so colleagues can view it at a later point. And please post your questions and on the chat section, and the moderators can bring it up as and when needed. And of course, at the end of the talk, we'll have a Q&A session where you can unmute and ask your own questions. So thank you all, and thanks, Anna. Over to you.
Thank you, Pavitra, and thank you for the invitation and for your patience in setting up this talk and scheduling it. I know it took a few months. So it's a pleasure to be to come back to this community, which I used to be part of for some short while when I was in IBM, right? It's a pleasure to share also the advancements in carbon-aware computing that I've been part of in the last several years. So here, this talk is, I'm going to describe what we mean by carbon-aware computing, what we do, how we grew and build the system and the community that is currently producing both systems and research and deepening the understanding what we need to do to decarbonize the grid. This work, like you will see, there is a massive amount of work right now, but it would not be possible without the support of so many people at Google and the team that has been passionately working on the topic throughout years. So I'm going to just provide a little bit of a landscape where we are today as a compute provider. When I say we, I mean Google, but I'm referring to large compute providers across the world. So first, this electricity demand of data centers, hyperscalers, for example, is really, really growing fast, especially now with the growth of not just computing, traditional computing, but AI. It's estimated currently to be around 1.5%, and there are different estimates everywhere when you read, but the fact is that it is the fraction of the electricity used for supporting computing is growing. And so as you probably know and read, and companies claim they are net zero, right, promises, contracted green generation that is typically used for like claiming net zero goals is not really enough for effective grid decarbonization. So this is the key premise and the key reason why we need to think about consumers' flexibility on the grid, where both workload flexibility, we need to think about that, but also market dynamics, electricity market dynamics, we need to harness to reduce emissions, right? So we need to think how supply-demand matching works on the electricity grid to understand really whether we are really reducing carbon emissions. So there are these differences between, how we do carbon accounting and how we actually impact actual emissions on the electricity grid. So all of these are really like the importance of flexibility led to the definition of carbon-aware computing. And now we say and AI, because this is in the workload that we are starting to think how to efficiently, effectively shape and manage. And we define it as exploiting flexibility in when, where, and how computing is done to reduce carbon emissions. So I'm going to proceed and give you a few examples before going into details of what we mean by flexibility, when, where, and how. And I'll, from time to time during this presentation, I plan to stop and to see whether there are any questions that I could really answer, maybe that address the potential concerns related to the fraction of the talk that I cover. So what do we mean by computing in when workloads, right? Flexibility in where they can run. So there are a lot of workloads that are not pressing, they're not user-facing, that we actually computing that we do to process data or extract feature, train models, run simulations that probably produce some decision-making tools that we use to control systems and processes. And these workloads can be done. There is no really this latency tolerance, and we refer, they can be delayed. Maybe they could be potentially scheduled in a particular time of the day when we want. And we call these workloads latency tolerant. And we refer to them very often as batch. So this was the first use case that we addressed, because at Google we know that these workloads are there, that we can control them, that they have some very loose SLOs, service level objectives. And you see the key idea in this context was, to ask a question, can we shift the computing to times of the day and better align the associated power consumption with green energy and electricity grid? So when it's sun shines and the wind blows. On the other hand, there is also computing which has flexibility in where it can run. For example, if you search, or when you look for Gmail and you want to open a Microsoft Office online, or you're on Facebook or Twitter or YouTube, there the latency does matter, right? But also these requests for these services can be geographically rebalanced. They can be met, but potentially by data centers not in the very near proximity of the user, but they could be there is some flexibility in when they are served. On the other hand, also, when large compute providers like Amazon, Azure, G Cloud, IBM Cloud, when they sell their resources, right, their compute, compute units and storage, they also, right, have an option user has an option to choose the location where it buys these compute resources. Since I think a few years, Google Cloud provided this region picker as a service, where user is giving an option to actually to come up and to choose and pick a trade-off between the latency and potentially like the greenness of the regions where the resources that it owns, the user owns, reside. So there are a lot of examples of these spatial flexibilities that we are going to discuss as well in this presentation. And the point is that this is even more powerful for carbon savings, because their data centers grids are very different. They are really backed up by very different generation mix. Somewhere we have more wind and solar, and even somewhere we know in some parts we have a lot of clean nuclear. So all of that really can impact the carbon footprint of the fleet, like Google's, that has data centers throughout the world. So is it completely new? And I cannot say it's new, right? This is an old idea, and academics wrote about it and built some small prototypes, played with it, think about green scheduling. And I'm just really like listing very small subset of this publication. What was not really never done, and it is like building. It was never the case that the system is built at scale. And it was never the case that really ecosystem like of Google or any large provider was addressed before the time when I started thinking about that, and this was 2018 and 19. So why? Because it's not enough, it was not enough. We couldn't really source knowledge, because this theory and these systems, this is new. We needed new theory, we knew to support the constraints that we see in real system. We needed data, we needed engineering to actually to support and build carbon aware computing. And so what happened? First, for the first time, I think in late 2018, 19, 20, all of a sudden there are some people, there are few startups. I have to say there's really literally small companies, startups that started providing carbon intensity data. At that time, it was the company called Tomorrow. Maybe now you know, it's called Electricity Maps. It's the second name of the same company. They came up with the data that and the underlying model that estimates the carbon intensity of each grid zones in many, actually not each in the world, but they had from very early on through their crowdsourcing models actually of operation and how they handle and source a lot of data across the world. They have a very decent coverage, right? And they could provide both the average carbon intensity data, this is how they started, and later on marginal carbon intensity data. Then on our end, it was convenient that we have these scalable infrastructures. And this is that when we design and build data centers, like they follow the same design principles, right? The same type of scheduling algorithms and admission controls. Everything is really operated in a uniform manner, no matter where you are in the world and where the data centers reside. So whichever model we came up with is completely scalable across the fleet. Then there are also VMs, virtual machines, right, that allowed us to virtualize, to isolate, to also to migrate. And this engineering work was instrumental to enable both running and packing VMs or different processes on the same machine for efficiency, but also migrating them to more power efficient, for example, clusters, to more power efficient machines or hardware configurations, or even to a different grid regions sometimes. So, and also what is important to understand what flexibility means, which workloads we can really touch. We cannot really shift temporally like workloads, jobs of users or user requests that actually, like for users, for example, that watch YouTube. This is no, this is something that is super latency sensitive. But at that time, when we started, we had a decent amount of computing that actually was consumed by workloads that are temporally workloads, as I refer to that as batch. So the actual publication came out only when we tested how everything worked, and I will describe the system that as we built it. Only, as you know, it takes then a few years to get to just have this outside and published. But our first announcement of the carbon intelligent computing platform that we built came out in April 2020. Then many large providers followed. Microsoft the same year with carbon aware Kubernetes announcement. Then in the next year, we announced how we are shifting some video processing workloads across the continents. And there are many more such efforts that followed, right? And I'm not even listing them here. I'll stop here, and I want to see whether there are any questions at this point before I proceed. No? Okay. No. So our vision is that we can use load compute flexibility to reduce emissions on the grid. And so we call this like, and we build these pillars really of carbon awareness, right? So, and the goal is really, it's not just like, you know, we are Google and we can build this, but it's also how do we increase the awareness of cloud users, customers, that they about how much energy and carbon footprint they consume. Then we also are trying to actually enable others, developers, people who actually do something with computing and give them power to actually reduce the carbon and to become more energy and carbon efficient. On our end, where I am most invested in is this building infrastructure for flexible load management, and also in work related to surfacing the engineering needs and engineering work to support really building the as large of a base for workload flexibility, because sometimes this is one of the hardest problem, the analytical problem that I worked on, like how can we really also increase the flexibility of our workloads, you know, shift them but still meet user expectations, right? So this is on a little bit on carbon reporting, and this is a screenshot of an early cloud platform that started publishing, right, carbon emissions of different users, and like for different compute services that they actually run in different regions, as you see. And this is a screenshot from 2021 when we really announced the tool, right? And in this way, users are aware of all of this, right? This is an estimate, and they can probably control and see the difference in, and actually through these, they can hopefully also manage their operations to reduce the footprint, because now many companies are in charge of actually and are responsible for submitting their environmental reports. This is a screenshot, on the other hand, of a tool which is called Region Picker, which gives you users an opportunity, or clouds, you know, people who buy resources, to pick a region. Do you want lower carbon footprint? You know, where is your traffic? Where you reside? You know, what is your customer base? You know, if you're building a business and you're buying cloud computing resources to support your business. So all of that is now really one port. This is a way to cloud source and to enable people to just, and companies and cloud consumers to become more carbon aware. But also there is this another one, and probably this is the most interesting part of everything. I find it most interesting is how we design a system, internal system at Google, that is going to, that manages workloads and manages, and in a way manages these allocations and runtimes of workloads, and in that way shapes the power consumption throughout times and space to reduce the Google fleet-wide carbon footprint. If you see here on this figure, this is really like I'm trying to overlay two grids in a way. One is electricity grid, and you see this transmission like towers in a way. These are transmission lines that are connecting everything. And then on the other hand, you have data centers that reside in different grids. Some of them are close to hydropower, some of them nuclear, some of them right are in the proximity of, you know, like, yes, coal and but in a way, and every grid region, because we have data centers across the United States, you know, Europe, South America, APEC, Asia, right? They're supported like with different generation mixes. And each grid is also operated in a specific way. You know, not all markets are the same, which is also so in order to really control the market or generation dispatch of a particular market, we need to be able to somehow, yes, we cannot mix up and mess up with system operators, right? But what we can do is we need to understand somehow or learn market dynamics and combine with our understanding of workload flexibility to really reduce the emissions of generation that gets dispatched right by the operators. And this is what our mission has become, and we understand that very seriously. So even though the first system, we call everything in general carbon intelligent data center load management, but the first systems are built with one type of signal, as I will mention later. We still are exploring what is the best way to respond to the signal from the grid. And this is an open topic, really. Like what's the most effective way to harness these dynamics, especially since the power data is very, very limited, right? And power data and grid topology is very messy. And this is typically very, very proprietary, only a subset and only, and at very coarse granularity. So why we see opportunities for Google Fleet in particular? So look at this. This is some example of 3 data centers, and they reside in 3 areas. One is in Midwest US, one is in Finland, and one data center is in Singapore. So this is just a 3 out of many. And so you can see that, for example, this bar chart shows 2 bars for each of these locations, data center location. The first blue bar is how many watts we consume per 1 unit of consumed CPU. The second bar shows how many grams CO2 of the carbon footprint is like really consumed. What is the food? This is the carbon footprint of 1 CPU hour. Carbon footprint is really an integral. It's like an energy type of metric, right? And so you can see in this graph that even for the 2 data centers, like the one in Midwest and one in Finland, you could have the same, we call it power efficiency, though even it's a power inefficiency, right? The larger it is, you consume more power for a unit of CPU. We have that the carbon footprint is much smaller in Finland. Why? Because Finland is a grid that is supplied mostly from nuclear and hydro. On the other hand, in Singapore is a grid in the country which doesn't basically almost at all have renewables. Everything comes from oil and really heavy, very, very, very heavy in fossil fuel supply. So we don't expect to do anything. However, we have a customer base in Singapore, so we need to have data center there. Obviously, we cannot just concentrate around green locations in the world, right? So on the bottom left graph of this slide, you see something else, another opportunity. And this opportunity says, okay, so can we control peak to average ratio of power in a power usage of a single cluster? What does it mean? Why? Because everything in the grid domain, and when we are also forecasting an investment into infrastructure, we are typically looking at peak metrics. What is the peak power? If the peak power is such, then we sign the power agreements with utilities, but also we use that number, like the forecast of the peak, to project how much power we need to invest into the power infrastructure, how much we can subscribe if not everything is used. So peak metric is also super powerful. So here we are showing that there is a variability of peak to average power ratio, and across different clusters, and there is opportunity to control it through shifting, right? And the top right graph shows you, again, these 3 regions, and you can see within a single day, the variations in carbon intensity. So sometimes we cannot move compute usage, right? We cannot compute usage from Midwest to Finland, right? Because we need to run this computing there. However, what we can do, and we can at least, for the latency tolerant workloads, we can shift them like to the middle of the night when we see a lower carbon intensity of the grid. So what I mean by carbon intensity, so smaller gram CO2 released from dispatched emissions for a unit of kilowatt hour consumed. So any questions related to these metrics? So, and this is how we approached. What was the challenge? So now we had to build a system. Now everything, we saw opportunities, we build a business case, right? We recognize that if we shift to greener times and to greener location, everything could improve. But how feasible that is? And so we needed to really like think about how the load management that we instrument must meet all reliability principles. Meaning, if you are sharing and controlling and pushing signals that influence load shifting, if something goes wrong, everything has to be discovered in time and rolled back in time. Then we have to think about infrastructure constraints as well. So, we cannot push and expect load to grow indefinitely. We have machine capacity constraints, we have circuit breaker limits, right? So if power all of a sudden spikes, we can really put the whole data center to dark. Okay, this is exaggeration because we have tripping the breakers that protect us from doing this. But I mean, yes, there is a lot of safety mechanism, but we have to plan and be aware of all these constraints. Then if you shift in time, the load is delayed. So we have to, even if you delay a workload, a job that you run, we need to have some performance expectations and guarantees. We need to understand when we do that the job also has some dependencies. It could be the job that produces some data that is then used by another job in the future. So these consequences of pushing could have been widespread, and we have to really have to be aware of what we push, and what we shift, and how, and by how much. And also, like, this was the key thing. Jobs have uncertainties. They are random, right? How much one job produce, like how much resources, compute units, memory, disk, network it consumes. It's going to change throughout the lifetime of a job. So these uncertainties definitely are something that we have to model uncertainty of each job. And we know that there are millions of such that are running. I mean, many more that are running at every second, at every moment of time in the fleet. So yes, this was not an option. First, the uncertainty is typically very large. So this is not an option to model a per job resource consumption and to manage it per that. And also, like, we had to come up with an approach to handle this uncertainty. And finally, like, these are schedulers, right? These are mechanisms. Schedulers are the ones who schedule or push, to decide where the job runs and by how long we push it in time. And so when we do that, these schedulers, because they have to make 500,000 decisions every second, so the simplicity of decision making has to be super low, right? Simplicity high or complexity low, I want to say. So the algorithms and signals and mechanisms to control the scheduler decisions have to be very, very efficient. But this was fundamentally what made our approach tractable, is the fact that when we started shifting these temporally flexible workloads that we want to commit needs to be done within 24 hours, we noticed that the total daily compute demand for these resources actually is something that is like a fluid, right? This fluid daily demand is quite predictable thing. And that we could just focus on predicting the daily demand and trying to shape it in a way so that we can control like this envelope in how much workload we can allow to run at any point of time. So, and we decided, let's compute the envelope of this intraday computing shape. And this is what was the key, and this is the fundamental principle behind actually everything. And it's now used across Google for many, many things, because so what we've done, we really didn't change the scheduler, didn't change the basic operational dynamic that happens, how the scheduling algorithms really work. What we've done, we actually came up with this analytics layer on top of the scheduling that is going to do a lot of things. It's going to forecast what is this inflexible demand that we don't touch, what is the flexible computing for next day. It will source carbon intensity from electricity maps. It's going to do really something called planning. And the output of this day ahead planning are going to be really these load shaping guidelines that are produced for each cluster across the fleet and pushed to each cluster. So you see here, for example, 2 places in the world, 2 clusters in quite different regions. The top cluster is in the region with, look, this dotted line, green is a carbon intensity, meaning that it spikes in the middle of the day, right? So, and the bottom has carbon intensity that reaches its minimum in the middle of the day, right? And so what do we, for example, in California, it has a lot of solar in the middle of the day. So what is the goal? So this red line is our shaping guidelines. So, and this would be the organic load, the regional load shape. So our mechanism is going to provide this guideline and say, okay, scheduler, you need to push this black, right, line below red line, as much as you can. But also what you can push, also shift some of the workloads that are spatially flexible also to the region with low carbon intensity in, at that time. So this is the key principle, and even every day today, and no matter, I will discuss how we enhanced our system, but this is the key design property. These are these load shaping guidelines that are regenerated daily and pushed to the fleet to control and impact. So what impact the scheduling decision? So schedulers today, instead of reading the true capacity of machines, they read these guidelines. They say, oh, for this top cluster, oh, I have less, I should just really stick to this lower capacity. I have less ability to schedule, which is really virtual. We call them virtual capacity curves. And they believing that and understanding that they have less capacity, they are going to do something with workloads, to push workloads, in time. So this is really the description. This is what is inside of the carbon intelligent computing system. So there is a lot of modeling that takes place. There is a power modeling. We had to build the models that really transfer, map computing usage to power usage. We had to develop forecasting methods for daily flexible computing and for intraday profiles of those workloads that we cannot run. And then all of these models, they go into this centralized optimizer, which is a global scale optimizer that then uses a bunch of constraints, capacity constraints, energy contract constraints, performance expectations, which are for example, meet all the demand within 24 hours. And carbon intensity forecast, these are these gram CO2, so consumed per 1 kilowatt, of power consumed on the grid that we source from the third party, from the electricity maps. Once the virtual capacity curves are computed, they get propagated to all clusters across the fleet when they start impacting, they start to impact the admission of jobs to to different clusters. And obviously we have also monitoring, and we are trying to see, are these curves too constraining? Because sometimes naturally and organically the demand for computing resources can change, in which case we need to, these models, even though they are refreshed, sometimes because the models, in order to be effective, we count on their predictability and low forecasting errors. But sometimes with abrupt changes and errors in the surprises in the demand change, we need to actually be able to detect surprises and to stop shaping for some time until we retrain our models. Any questions regarding this system?
Anant, I know you had a question. Do you want to ask that first? I can follow up with mine.
It's just a quick question. I first posed a question about, is there variation intraday, and then you actually got to presenting it, and so that. But I was surprised that the intraday pattern is quite different among the different regions. For example, the carbon intensity, if I read the graph correctly, in the Midwest, peaks in midday. Finland peaks at night. I understand that's not central to the optimization, but I was curious why we see such variation.
Okay, first, you have to understand also that they are put in the same time zone.
Oh, okay.
Right.
Okay.
Right.
Okay.
There are quite different time zones, but we operate with this data, right? So the beginning of the day for the optimizer, and you see that we had to think how to patch that. It's not that,
Yes.
when we were thinking about, day ahead forecast, like for us, day ahead will start a different time, it will be probably start at 0 time for Pacific, because at Google everything is Pacific Central Time, the West Coast is the central zone, right? But everything else is really shifted with respect to that, right?
Okay.
There is
So
that influence.
they might actually be occurring at the same time of the day locally.
It might, but also that is one reason. First, important one, because there. Another, that the grids are quite different. For example, Finland has a lot, it has wind, right? And wind, nuclear and hydro. Nuclear is quite, and you see that it has smaller variations, right? Finland than other ones, because nuclear, with a massive amount of nuclear, you don't redispatch nuclear. It's just really, really like a stable, right, workload. All variation will be handled through wind in the grid, through wind and hydro. And you see where we put the hydro increased in wind production for Finland. This happens at 9 Pacific time, which, what is this? 9 Pacific time, it's like late afternoon in Finland. Right? So there are different patterns, right? For Midwest, there is so much coal, right? And it really, you see it ramped up in the middle of the day, coal and gas, right? Combined cycle. So, right, it really is very much driven by the generation mix and grid operations itself. Electricity markets, right? Did I answer your questions, Anand?
Very well. Thank you so much.
Yeah.
One more question, Anna, which I had was in the optimization forecasting slide you were sharing. Do you I mean this is solved? Yeah, you were saying once a day, right? Like, or every. So how do you handle any kind of recourses, or do you manage recourses? Like you said, there were potentially surprises and other things, right? So how do you shape it on the fly, or do you shape it once a day? Yeah.
We cannot, because of reliability principles, unfortunately. So we need time even to push these controls. But we count on the fact that we can we don't use point forecast, right? We used a high percentile of the demand forecast for the next day. right? So imagine that we forecast like, and we can do that and be still effective because our forecasting and, you know, is quite, actually, we claim very low forecasting error. So this 97, for example, high percentile, you know, allows us to mitigate these risks that you say, you know, that you mentioned. So
Got
they
it.
are very, for us, they are, so when we plan, you know, how much capacity, and I will show you something, we can allocate to a cluster, right? And reshape, and how much we need to provide for the whole, you know, reshape throughout the day. It's not really like expected value, it's a high percentile. So we are with high probability, very high, we're actually meeting the whole demand and still managing to shape. And you will see some examples, right? So, but if we see very drastic courses, as you mentioned, then we detect them there. We have even an SLO on that, to be honest. We had to write all these, like what happens in which scenario as a rule before doing a launch. And we say, okay, we are not going to have a recourse of that kind or violation of that kind more often than once in a month. Very often we don't see, you know, in any cluster of the fleet, right? So it's very, and it's been running like that for what, how long? It's like 5 years. Yeah.
Thank you. Sridhar, want to ask?
Yeah, thanks, Anna, for your talk. So in academia, people talk about imperfect computing, right? Which is, you know, do you really need to get the answer right? And so you can save a lot of energy by, you know, just getting approximate in internal methods. I mean, again, they're theoretical, but, you know, they don't translate necessarily to chips and things of that type. But then analog computing has been talked about for decades, right? Photonic icing, you know, things to add on to the chips. I know that Google and others have been looking at this. When I looked at the efficiency in Singapore, I assume they're using more efficient chips, or they're choosing not to use GPU chips or something like that. I was wondering if there is any long-term view on not relying necessarily on digital computing, you know, which has limits really on how well it can, you know, scale with respect to energy.
I'm sure that I cannot give a say. I know that the people are exploring every possible way how to reduce and increase the efficiency, and the approximate methods and non-complete, and like everything is what you mentioned is very well discussed. I don't see that we are going to depart soon from digital computing, right? So I can only say that, you know. So, but in a way, I also see that we accomplished huge energy efficiency gains, and some are going to happen soon, right? Even in new set of publications that is in preparation, that are going to still come from this type of management, right? This type of compute control, you know. So we will try to squeeze every unused resource as much as possible, right? And still preserve. This is the North Star, right? Vision for us, and still preserve really like. The guarantees of expectations from workloads and users, right? I don't know whether answers. I you know, I cannot. I haven't been part recently on more on the discussion of analog computing.
Yeah, I think the future, at least the way DARPA and others are doing now, is changing clock time to compute to energy to answer. They want to know what is the energy being spent on getting to
Yes.
the answer,
Yes.
and then trying to see if analog-based devices can start doing special computations and things of that type. So this could be 20, 30, 40 years out, but but
Yes.
that's the kind of thing that we had to fundamentally get away from the transistor 0, 1, you
Yes.
know, kind of discrete world, right? So anyway,
Yes.
so, yeah.
So
But
I would, sorry to interrupt, but I know we have about 10, 12 minutes, Anna. So if you
okay.
have, if you want
Okay.
to, we can continue the discussion, maybe the questions after you finish your full talk. Yeah.
Sounds good. I just want to add, whatever is the future, I think all this methodology will be able, you know, about how to model compute, whatever it is. I think this is scalable, transferable fully. So for example, when we focused on this, we worked in the area of pure computing, no AI. And now we see how many things are really applicable in AI, at least batch or training ML, So, so what makes this approach effective at Google? So what I can say, right, really first is predictability. If you want to have effective controls, really we need to understand it, like, right, that to forecast demand properly, to map compute usage to power. And as Sridhar said, yes, we also really are expressing our metrics more and more, not in compute efficiency terms, but more power and carbon efficiency. This has become really one of the key business metrics when we are reporting the benefits of a project or the impact of the project. And, we needed these average carbon intensities, as it was mentioned, like this is a necessary data. I mean, I'm not saying that this is average, and I will mention the future and our focus, also one of our focuses right now, but this is a grid signal, right? So also the scalability, whole approach, if you see, everything is very uniform. I mentioned this like small graph, but we cover with all this suite of analytic pipelines, we cover the whole fleet, and we are able to control tens of data centers, right? So we have a scalable optimization framework that uses aggregate demand, estimates capacity curves, and pushes these capacity curves fleet-wide. It's computationally efficient. The models get retrained, the optimizer reruns in no time. We kind of made sure to reduce the computational complexity and provide this really to be able to understand, also to have a optimization framework that is also really explainable, very important. And also, risk awareness is important. Our framework does incorporates explicit workload performance expectation. We have really like a prediction uncertainty playing a role in resource and power demand, all power infrastructure limits, energy contract limits, everything was part as just simple to add constraint. And we have many other infrastructural constraints. Since we pushed this, I think that people figured out that this can solve a lot of problems across Google as a framework to control power and peak computing, and it's been just scaling. So this is just the basic things that are optimizers. Objective, can be simply put as a co-optimization between these two terms, where we have two weights, right? We have carbon cost, and we have peak power is kind of also infrastructure cost, because for every unit of increased power, we kind of have to, in a way, we can probably marginalizing. We have to plan for more power, infrastructure support. But these trade-offs allow us to really evaluate what is the carbon cost for Google, and we have different approaches internally. And and this optimization, as I said, happens every day. And I have to say, these two do not have to be, in some cases, in some grids, it will turn out to be, they could be in opposition, but most of the time, like sometimes efficiency and carbon goals can align. Right. So I will show you some real stuff. And this is why when we write our papers, like why we are Google. So we have to to write really about and expose real data. So I'm going to show you how the amount of flexible load in a cluster, how the prediction uncertainty, and how variability and magnitude of carbon intensity affects the shaping and virtual capacity curves, right? So if you see, we have three cases, right? And the top left case is a case where you see a large variation in large uncertainty in flexible demand, right? On the other hand, we see also that this blue is really it's a normalized compute. So meaning that if one is the full capacity, you can see that it reaches 80%. This is a lot. So what we can do, you see, we push this a red curve, and you can say, oh, there is so much space. I will mention more later under this red that is not used, but you see also the effects of dropping so much, like pushing it down here. And so at the time of the day where this black line, black solid line is carbon intensity of that local grid, is really the highest. And you can see the impact, which is 8% of is power. We see in this cluster 8% of power usage drop for 3 hours, meaning, you know, it's a very solid demand response. And we still preserve the total throughput of that cluster of a day. You know, here on the second one, we see, you know, this is what you asked. So we cannot, it's not easy to get surprised here, right, Pavitra? You see how much room we leave really for load to grow because of large uncertainty, right? So for the other, like this second use case, you see how it's a smaller gap between the actual load and capacity curve. And you see how we drop. We also, like, we have a significant drop in the time of the day when the carbon intensity is high. And, but you see how nicely, like how effective this mechanism is. And we can do that for 6 hours, right? Imagine how much utilities can, and we had such scenarios. I didn't list it and reference it in this presentation where we were actually helping local grids by dropping power in some times of the day when they were under stressed. The last scenario that we put is high uncertainty, small flexible usage, where basically this shaping in this case is really, really not meaningful. So it really will depend. In some cases, we will be more or less effective depending on the amount of flexible load, the uncertainty in the demand, and you know, also, right, and like how much flexible, you know, usage and everything we have. So here is one like data center, like normalized data center load shape for a selected data center. And so you see that this is the carbon intensity. This green line is the carbon intensity of the local grid. You have a blue line, which is the original shape, and orange, a load reduction. So this, you see the really actual effect of dropping power through dropping computing. So open challenges to wrap up, right? I have a few, but first really is, and only when you start controlling flexible load. Before we started doing this, I think that like infrastructure and engineers were really always, because they're supporting users, you know, it's always a fear, oh, we are going to harm them, and, you know, we can mess something up and we can lose users, you know, they can lose trust in us. So, you know, yes, when we started doing this, we originally had complaints. We had to explain the methodology. There is a lot of work to socialize the concept and socialize why we pushing workloads later at time. Even though these workloads didn't really, and users didn't really have SLOs, we needed to explain. So also to explain why these effects and whether they are ready to or if they're not happy with what we do, they have to move and change the tier that they run in, and to pay more, right? So also, like there is an open challenge, and we are going to soon really, we are writing right now about that. We pushed the system, but it has been taken a lot of time to spatially shift workloads. This is even harder, right? So finding the right location, taking care of all right resource demands, that you have enough network, that you have enough memory in the destination GCUs, how you handle these cross-resource moves, how you figure out and classify workloads as flexible and so on, spatially flexible. And also the hardest maybe challenge, which while many people are probably truly thinking about that, if we are going to like scale up and see what is the global problem, and this is the problem of grid integration. So what do we do with this? Are we truly effective today, right, on grid level emissions? And how can we produce, are these guidelines that we produce really like scalable? You know, could we say that if everybody followed this, you know, their way of shaping, but following these carbon signals, could we claim that we could really have a meaningful impact as together, like, you know, as a bunch of compute providers, a Meta data center, Google, like doing similar things? This is something that you probably are aware is people who do a lot of cross-resource and resource allocation problems and working in this area, you know what it means to have resource stranding. You know, you can be, you know, some capacity it could be completely ineffective in like a fraction if there is, you know, if we cannot meet the demand across different resource dimensions. And this is the problem with, you know, understanding the CPU storage network accelerators demand and their cross-resource correlation. If we don't manage stranding well, and shifting can also help stranding, because if we are doing smartly selecting where to run, we could be reducing the amount of this unused capacity. Another one is, I'm just skimming through this, understanding the impact on different performance metrics of jobs that we shift across space and in time, their disruptions, their queuing latency, what is the probability of their disruption. So we have a monitoring dashboard where we try to do that exposed to users. And also, right, this real-time placement also, you know, so it's always, right, a trade-off. So, but I think that from now what we see along the way, we learned so much that you know, we have our hard times and and we had to sometimes revamp, change algorithms, really you know, loosen some constraints, but everything, you know, there is always a trade-off with what we expect and how much carbon we are going to reduce. But these are always like tuning, and this is why we have to have control mechanisms that are going to really like monitor the system health and you know, provide the feedback to the decision, the subsystem that makes decisions. How many minutes do I have, Pavitra?
We are out of time, and I know some people have already dropped. I mean, we have more time on the calendar, and if people want to stick around, they are welcome to, and we can go through the Q&As as well once you are kind of at a point to stop, Anna.
I can stop. I will leave this slide. This is really a really open problem, so I wanted to leave it this way. And for yeah, I can take questions.
Okay. Yeah. Thanks so much, Anna, again for your talk. A couple questions here are, let's start with Nicola. You want to ask your question on the...
Yes, I'll be brief. Thank you.
Yeah.
Anna, thanks for the presentation. Very interesting. I was wondering how much own generation there is, because from the slides, it sounded like all this load was being covered by external power from the grid as opposed to own generators. And I was thinking about different providers like Amazon, for example, that seems to be using quite a bit of its own generation, in which case you can control emissions much more directly.
So thanks for asking this question. This is really one fundamental ones. Being covered means it's typically is something that is used for accounting purposes, not truly emissions. Being covered means that we invest into green energy somewhere on the local grid, not attached to the data center or Amazon or Meta, right? So that we kind of to be as close to the consumption of a data center in that grid. You know that the grid is a network, so really we always consume the grid from the energy from the grid that we are connected to directly. It's not coming from that PPA, right? But the investment itself contributes to the right the clean energy, right, fraction of the grid overall. So we do influence the carbon intensity, but not so directly. So how much? It depends on the region. Some region, and you know, we are all compute providers are thinking about this because we need to submit these environmental reports. When we build data centers, there is this energy location strategy which incorporates this grid signal and what is this grid good for investment in wind, solar. Now, recently, we started investing into nuclear as well, right? So how much? In some grids, we are not covered by this at all. Like in Asia, there are very few these PPA projects, so we cannot, like in Singapore. So they're really like probably what makes us like and some other companies that need to have a data center in dirty location to support their customer base. Yeah, we have to think about different solutions of reducing our footprint, right? Yeah.
Thank you.
Thanks, Anna and Nicola and Nitya. Would you like to ask your questions? I think the others are mine, so I can ask later.
Okay, sure. Yeah, thanks, Anna, for the presentation, for the talk. Which compute resources do you use for the calculation of carbon? Is it only CPU or is it more?
We found out that the biggest, and there is a paper you can find. Early on, it was so it's mainly driven by hardware configuration, platform configuration, compute units, CPU, and accelerators of TPU chips. Accelerator usage, not usage itself. Yeah.
Okay. And in the example of the data center where you showed the drop, I was wondering if that load, did you just drop the load or did you actually migrate it to the efficient?
It went to later time. Yeah, we preserved.
Okay.
Yeah.
I see. Okay. Okay. Understood. Okay. Thank you.
You're welcome.
Thanks, Nitya. Thanks, Anna. One more question. I mean, two questions from my end would be, how do people specify flexibility? Like a load is flexible. Do they know how long a load will take to compute, or like how much usage it will have? Do they profile loads and only those loads are flexible? So how do they even specify it? So I was curious.
Yeah, that's very good question. They don't spend. Okay, first, there is a specific tier for workloads that have no strict guarantees, and we treat all of these workloads, we call them best effort, as temporally flexible, right? And we created there are people who really like work on infrastructure that created guidelines and say, okay, we are going to shift you, but we promise that everything that runs in this tier is going to be completed within 24 hours. Okay. For spatial shifting, the system operates like that users don't profile, they request resources, but they also request to be placed, they register, like they don't specify a location. They register through a component of a system, in a way, how that, and through a way, by going and submitting requests through that system, they are inherently claiming, treated as spatially flexible. And this is how we basically operate only on those workloads that do not specify locations where they want to run, but they actually request to be placed through that system.
Do they get brownie points internally to get to say that they can move their workload?
This is why it was very important that when we do this, when we show that we didn't harm their performance, that we actually improved.
Okay.
And we showed the improvement in performance, then this is a great sell. Then you build trust with users, right? And why? Because we always provide this more capacity to greener locations. So if you can be blind, you don't know, you as a user don't have to monitor the system. But if our system makes sure that you land at the location with more availability, and these should be correlated with carbon intensity, right, itself. So yeah. Then you should expect better performance. Yeah.
Okay. That's good to know. And one more question was around infrastructure cost. You were mentioning that you're trading off between infrastructure and carbon. Isn't data centers already like a capital cost invested, or you're looking at some kind of marginal I mean, what is infrastructure cost in that sense for
Yeah. It's very good. So for us, there is inherent inefficiency, because when you run jobs, even if they lock some resources, right, or machines, even though you never run machine, you cannot run any machine at 100% utilization. Right? So for us, like, what it means is that this is called power over subscription. That if we can push the peak usage for that high guarantee of non-used capacity, we can put more machines in that data center to leverage this inherent inefficiency, right? So in a way, we are trying to run for a given data center and for a given, power infrastructure capacity. We are trying to really support as many users and as many machines off of that. And by controlling peaks, right, and managing to run everything squish within the LS, we can run more machine at that lower utilization. So this is called like oversubscription. There exists oversubscription of computing, and there is oversubscription of also power infrastructure. Right.
That's very interesting. Thank you so much. I know we've taken extra time, 10 more minutes, and any other questions that anybody else would like to ask? Yeah, if not, Anna, thanks so much for
Thank you for your patience with me, and we'll stay in touch.
Yeah.